Okay, sorry, I'll start again. So anyway, we should be wrapping things up by Monday, and then we'll have a test on Tuesday. But whenever you're talking about measurement, and that's what this unit's about, we had a little bit of history of the measurement, where the metric system come from, all that. You have this project based on the Earth. I'm hoping that, if you haven't been out there yet, it's okay. It's probably going to be cloudy today, but maybe sometime in the next 3 or 4 days it'll be sunny. But you can't keep putting it off. You keep putting it off, and then what if you get, cloudy days? So I give you almost 2 weeks to do it. So I'm sure you can get outside once in that 2-week period. All right. So anyway, we're talking about measurement, and sig figs don't even come up unless you're talking about measurements. And so measurements contain 3 things. They contain a number, a unit, and error. And the number is the sig fig part of it. You get it? How many numbers? And you know that it depends on what instrument you pick up. Is everybody with me? When you guys do your labs, I'm going to require that you write down sig figs, meaning if you pick up that graduate cylinder, you need to write down every one you're certain about because of the lines, plus what? Plus 1 guess. Now, the good news is we have an electronic balance. The electronic balance has a little computer chip in it, and it does it for you. Now, if everything in the world, even measuring lengths and volumes, were digital, I wouldn't even have to teach this anymore. Because somebody would have built that into the computer chip, and they would have actually rounded it for you and all that kind of stuff there. So if you use a digital balance, it's just going to give you a number, 13.55 grams. And you don't have to worry about it. That's it. That has 4 sig figs. That's it. All right, so anyway, another thing that happens, though, these 2 words that always show up when you talk about measurement are accuracy and precision. Now, a lot of people think they're the same. Let me ask you this. If I took 1 reading, could I tell the accuracy of that? And could I tell the precision of that? Both of them? Neither of them. Let's talk about that. So let's say you did an experiment. You did it once. Could you tell me about the accuracy of that 1 measurement? Yes, if what? If, somebody said, if you have the target. What's the target called in science? The true value, accepted value, the given, the known. Everybody get that? Standard. So if I give you the bullseye, instead of saying target, say bullseye, because, all right, bullseye. If I tell you the known, then you can tell me with 1 reading, you can tell how accurate that is, right? But what about precision? Precision has nothing to do with the bullseye. It has to do with how close a set of data is to each other. See that? And that's why when you were doing the percent error, let's see, I can find it here. When you were doing the percent error equation, everybody have that down yet? Have you got that down? Okay, I know I'm going to ask you that. Then we had, whoops, where am I at? There we go. I'm not sure, did we get all these done yesterday or not? Did we get this table almost done? Okay. So when you're doing the percent error, we find the average for the student, and then you had to have the bullseye, the true value, and then you found out the percent was about 0.123%. And that's really good. Honestly, sometimes in physics, under 10% error is good. Under 5 is really good. And under 2 is like phenomenal. It all depends on what you're measuring. Okay? So this right here would be a phenomenal results. And then this student also had phenomenal results. It just so happens that the one who has the least amount of error would be the most accurate. So I'm going to give a little bit of nod here, but both of them did a great job. Now, you're saying we did finish average deviation or not? Okay. Did the other class that didn't? Okay, so the average deviation says, and this every year when I give this test, the reason that a lot of people miss it, I don't want you to miss it, is they think that you find out how far away you are from the given. That's not true. You don't use the bullseye for that. You find out how far did you deviate from your own average. Can everybody remember that? Because I don't really care about the bullseye. I care about how close are they to each other. Okay, so anyway, what we found out was that this person, wow, on the average, their high and low values are only about 0.2 grams away from each other. That is also phenomenal. It's a 73-gram object, isn't it? They're doing something right. Whatever instrument they're using, it's very precise. And even though it's very precise, look at this one. That's unreal. That precision is way up there. You get that? So I'm going to give the nod for the most precise to this student here because they have the smallest average deviation. Okay on that? That's not bad. Pretty easy. All right. Well, now, what I'd like to do is, I have some pictures, and that's up to you to do these, but I'll do one for you. For example, here's a ruler. Very typical question. I have a ruler on the test, and let's say you're trying to do right there, G. Let's say you're trying to do G, right? And you said, and this thing's in centimeters. Let's say that the ruler's in centimeters, and here's the letter G, and I say, well, there's 10, there's 11. I bet 9's over here somewhere, right? So you say 9 point what? And the good news about these companies, they about halfway across, they put a bigger line. See that? So that's 9.5, isn't it? What's this guy? 9.6. I am certain it's 9.6. This ruler, I start guessing where? Centimeters? Tenths of centimeters? I mean, tens of centimeters? I mean, centimeters, tenths of centimeters, or hundreds of centimeters? So I have lines for tenths, don't I? So I have to guess hundreds. So I had to put another number here. And, you know, some of you think, well, I don't know, that's definitely more than halfway. I want to say 7. But what if anybody else thinking something different?
I think it's 9.68.
All right, I'm all right with that. I'm all right with that. I know that last number is you know, the guess anyway, right? So I'm not going to do a lot of these, but you can practice with that. Now, look at this right here. Some people get tricked. On F, you say, well, that's 12. Well, then you don't know science, okay? Let's try it again. That might be 12 to somebody who's never had this lesson. But I know that ruler, you have to guess hundreds place. So you can't say 12, you have to say what?
12.000.
Now, I'll give you a little clue. What if somebody thought, I think right before the 12, what would you have put?
11.9.
Well, then why would you only put 2 up here if you would have put 4 here? See that? It's the same ruler, isn't it? So anyway, I have I don't know, 3, 4 questions on the test where I show pictures of graduated cylinders. And even though we had this in 10th grade, I'll go over it one more time. What part of the meniscus do you read?
The lowest.
The lowest. And so what you do is you try to figure these out. And so here's, what is that, 30? That's 30, and that's 35. Wow, I wonder what each line is. Be careful. Be careful about that. If that's 30 and that's 35, what's that? Is that 31? Let's try it. 31, 32, 33, 35. No. 30 what? 30, 30.5? 31. 31, okay, see that? So this is 31, 31 and a half, 32. Okay, now here's 33 up here, right? Now, even though we have a line for halfway, we can't be certain about which place. Can I be certain about the ones place? Yes. But I still have to guess hundredths place. So what do you think here? 32, this is 32.5. So what do you think? If that's 32 and that's 32.5, then maybe it's a little bit more than halfway to the halfway. What's that mean? A little more than halfway to the halfway. What would you put there? 32 point what? 8. Here's 32.5 right here. 32.5 is right here. Maybe 3. The bottom of meniscus? I think the bottom meniscus, you might say 8, but that's up there pretty high if you say 8. Oh, 8. That's way too high. 32.3, you can say that. Here's 32.5. That line is 32.5, isn't it? It's got to be less than that. So 32.3 maybe? Maybe 4. I'll be all right with that. I'm not okay with 8. I'm not okay with 8. Anyway, so I'll have you do that. And that, excuse me. Here's an article, even though it's 1995, I know it's a long time ago, and if somebody wants to update this, if somebody wants to look this same article, not the same article, but if you want to update this for me about how they're doing, they were talking back there that how they really do need measuring rulers at the really, really small level. And if they do, the next big jump in technology will occur. If you thought computers used to be size of rooms, and then they became size of desk, and then they became size of your phone, all right, what's going to happen if we can start measuring at even a smaller level? Can you have computers the size of grains of sand? I don't know why. Why couldn't you? Now, the keyboards would be small. Just kidding. I'm sure you'd be able to talk to, voice. But anyway, they could make computers much, much smaller if they had a way of measuring small things. And if they were going to make something, can you measure to see if you're making them identical? So the next big jump in technology will occur with a jump in measurement. So if somebody wanted to look up anything about this and anything you want to update, I wouldn't mind replacing this article with a new article, if you can find it from. Okay? All right. Now, a small assignment for you for Monday. Small assignment. It's kind of fun. I don't think we did this in chemistry, did we? Okay. I had a student many, many years ago, and they wondered about the idea of accuracy and precision, and they wanted to know, is there a way that you could, without mathematics, not to use mathematics, but could you find out something like this? And I said, why don't you design a lab? Why don't you design a little mini activity where somebody could explore precision and accuracy at the same time? And so, even though I modified it a little bit, what they did is they drew the bullseye, and notice that they decided that would be 10. If it's outside here, it's 10, 5, 3, 1, and minus 2. And it's just like golf. In this case, the lowest score is going to be one of the best ones. But they want to combine accuracy and precision. So look on the back here. Sometime in the next 3 days, you have to find somebody who can help you. Now, you are the commander, okay? This paper is about you not being the robot. You're the commander. Everybody got that? So you find somebody who's going to be your robot. Now, look at the rules. The goal is to be able to compare accuracy and precision while playing a game. The objective of the game is to attempt to be both accurate and precise in order to achieve the desired score. So what you do is, if you want to use a real sharp pencil, you could. I've had people that they went on the back of their deck and they happen to have some darts, and that worked. I had people that had markers, felt tip markers. They make a nice little dot, but somebody's going to drop a pen, and you got to be able to see where it hit. So you can figure that out. Is it going to be a marker? But now the next thing to do is pick one person to be the robot. That's not you. The other person is the commander. Begin by having both people have 3 markers, and you're away from the target. Now you have to blindfold the partner and allow them to have a marker, and then once you have earned their trust, spin them around 4 times, and then stop them wherever they might end on the 4th revolution. Now this is important. You can't be next to your robot. You have to be at least 2 meters away from your robot. 2 meter sticks, okay? So that's about like you and I. So the target might be on the ground, and I cannot come up next to you. I can't come up there and put my eye right over the pen and say, drop it. You get that? So I have to give you commands. Right, left, right, left, 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 right, right, stop, forward. And then when you think it's ready, you say drop. Okay? So it's your robot. Then what you do is, after you figure out, let's see, here. The markers should have the lid off. Yeah, there we go. She wrote that. Repeat this thing 3 times. So you gotta do the same thing 3 times, and then when you bring it back, we'll find out who was a good commander for their robot. Now, if you wanted to, this is up to you. If you want to have a blank piece of paper and maybe do a little practice runs, you said, I think I'm ready now. I think me and my robot, we got it going here, okay? And then you put this one down like that. Now, here's what you do. How do you get a score? It says here, scoring. There are 2 categories that contribute to scoring in this game. The first step is to calculate your ultimate score, is to measure the accuracy of your points by using the scoring values on the thing. Now, this is easy. So, for example, if you have a dart, So if you have a first dart and it lands here, and then another dart lands here, and another one lands here, well, that's the easy part. You simply say 5 points plus 3 plus 1. Now, as far as confusion, I'm going to say that if any part of the dart, if any part of the dot is in this thing, even if it's like on the line, but any part of it is like there, then I would go ahead and give you the 3. Everybody get that? Okay, all right, there you go. So that's the easy part, and then you add that up, and that's your accuracy score there. But what I think was interesting, and this is where she and I kind of talked a little bit about, well, you could get some pretty good points for accuracy. What if I get 1 here, and then 1 here, and 1 here? That's still not a bad score. That's 8, because I got the -2, right? One of my darts is pretty good. But you should pay a penalty for that because they were pretty far spread, wouldn't they? So here's what you do. You take a ruler, a centimeter ruler, okay? Don't tell me you don't have a centimeter ruler, okay? Centimeter ruler, and you have to draw lines between your things. Now, on here, I would draw it, put my centimeter ruler here, and that might be around 4 centimeters. And then I have to go from here to here, and I have to go from here to here. And what you do is you add up the number of centimeters for the perimeter of that triangle. And see, if your triangle is really big, that's going to hurt your score, isn't it? It's going to make your score bigger and bigger and bigger, and that's what you don't want. But what if somebody does this? What if they go like that? Now, they might get a 15 on this, but they're going to get a tiny score on this, aren't they? Anyway, so I thought it was pretty good how she kind of meshed the two together and how she came up with the scoring, and she came up with the idea of using centimeters, and then you put your final score here. Does that make sense to everybody? Okay, so I hope you, that's just something fun. I'll give you 15 points for it. It's not a big assignment. It's kind of fun. If you ever want to do something different, you say, well, I have an idea for another project. Let me know if you have an idea for something else. You okay on that? I'll put that on Google Classroom, and I'll say I'm due on Monday, and it really won't take too long. It all depends on whether if you want to practice with your robot first and then do the real thing, you can do that. All right, what I want to do now is we're going to go to this part right here. And we had, even though we did this in the 10th grade, by the time you do this again, it should be pretty good. You should be getting pretty good at the temperature scales. And so we're going to talk about this, and you are allowed to use your calculators, right? Remember, every test from now on, you're allowed to use your calculator. So if you have a calculator, let's go ahead and get that out.
Teachers and students, please pardon the interruption. Cross country, there is no early dismissal today. So cross country, no early dismissal. The meet has been moved to GDS at 4:30. Thank you.
Okay. Anybody here cross country? Oh. Don't be ashamed of it. I like cross country. That's a tough sport. That is tough. All right, let's take a look up here, and let's take a look over here. So what we have is, I'm going to show you, I'm going to have a video. I'll probably post a video maybe on Monday, and somehow I want you to be able to see it. But the history of temperature scales, it varies. You know, like at one time there were like over 200 different temperature scales, depending on what little city or what little town you lived in. And each scientist might have had their own little scale. And yet right now, I would say the 3 that survived were the Fahrenheit, Celsius, and Kelvin. Everybody get that? I know you don't like me saying this, but almost nobody in the world cares about the Fahrenheit scale. Okay, I just got to tell you that they don't really care. If you go to Europe, if you go to Italy, somebody say, hey, what temperature is it? And they'll say, what? They'll tell you a temperature. You say, well, what is that in Fahrenheit? They'll say, I don't know. They don't really care. So essentially the whole world uses the Celsius scale. Okay? That's the way it is, period. If I walk up to somebody from Africa and I say, what's your normal body temperature? They're going to tell me 37, 36.9. It's like, what? How do they know that? All right? That's what they've always heard. What if I ask you in Fahrenheit, what is normal body temperature? What would you say? 98.6 actually, but that's all right. And do you know that some of you Some of you, that's not your normal. Your normal. Some people are like 96.5. That's like they feel healthy. It's just they don't get up to 98.6. Happens. Okay, so let's go over here, and the first thing I'd like you to do is let's look at the Fahrenheit scale, and that's the one you're supposed to know. Everybody in here, because you have snow days, you know that when it gets 32 and there's some kind of precipitation that night, you know that you might not go to school the next day. Is that right? So that's the magic number here in the United States. And then very few of you know that water boils at 212. It's kind of a weird number, isn't it? Kind of a weird number. So those are probably the two you know. And then you also might know 98.6. Okay, and that would be body temperature. Okay, so normal body temperature somewhere around 98.6, okay? Would you say that's probably what you know? I would say some of you probably didn't know 212, right? You probably knew 32, is that right? You probably knew 98.6. If I ask you what is absolute zero in Fahrenheit, the chance of you knowing is pretty small. Okay, what is it? It's very close to, minus 459 point blah, 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 blah. It's very close to minus 460. You get that? Okay, so somebody said, wow, it's like 800 degrees below zero. No, there is no such thing in Fahrenheit. See? Okay. Are you okay with the Fahrenheit scale? All right, let's go to the next one. When they made the metric system, they wanted to have a temperature scale that was also based on powers of 10. And if you think about it, this is pretty smart. They thought that water was a very important material. And they thought, even in the laboratory, water freezing and water boiling, that's what two big important events. So they wanted to put those, and they could have made it 1,000. They could have made 1,000 degrees between them. You get that? Again, then humans would be talking about, what's your temperature? 855. Humans don't like that. Humans like numbers between 0 and 100. They do. So they said, we're going to make it as a matter of fact, when I was your age, no one called it the Celsius scale. No one, no book. It was called the centigrade scale. Each graduation grade, get it? Each graduation was 1/100th of the way from the boiling water to freezing water. So anyway, the good news is the person they wanted to honor, he's lucky that his name started with a C, and they didn't have to change any of the books. Degree C, degree C. Pretty good. All right. Well, anyway, so we have 0 and that, and I think most people know that. But I'm not sure you know hardly anything else about the Celsius scale. For example, even though I told you what it was, we're going to calculate that. What is body temperature in Celsius? Even though I told you, we're going to calculate in a minute. And what's absolute value? What's absolute 0 in Celsius? A lot of people don't know that. They just don't know it. So we're going to play with this for a little bit, and then we'll get to the Kelvin scale, okay? And so what we have is a little chart down here, and we know that this is this. And how about room temperature? Would you say room temperature, some of you like it 70, 72, some of you like 74, what do you like, 72? I would say most people think 72 is pretty close to room temperature, right? Okay, so what we're going to do is, and I told you a story before, and I'll probably sing the song one more time, but it's not even a song. It's like so short. I wouldn't call it a song. Would you call it a song? Yes. It's not really. It's just a mini rap. Rap. So I was rapping before the rap. But anyway, it's not even a rap. Okay. So we'll do that in a minute. We'll do the song in a minute. But I noticed that a long time ago when I was trying to be a science teacher, I said, well, at one time I only taught this at the beginning of the year, and I never used it after that. And next year I had to learn. I just got it out and memorized it for that day. See that? Then after a couple of years, they said, it's kind of dumb, you know. I'm a science teacher, and why don't I memorize these? And so I looked at them and I said, how am I going to memorize those? And then I started looking at it like this. And it says, I looked at this one, first of all, because this means you've been given the Fahrenheit. And I'm going to change it into the Celsius. See that? So I looked at it and I said, well, I live in the United States, and they're probably going to tell me the temperature. Today's temperature is going to be around 70, about the high of 70. So if I want to calculate that, this is probably what I need to learn to change it to Celsius. And then I looked over here, and see, I noticed, look at this right here. Notice that in the parentheses, you do this addition subtraction thing first, don't you? Then you multiply. and you use 32. Now look over here, what happens? You do the multiplication first, and then you do the addition and subtraction first. And here I subtract 32, and here I add 32. And I thought, wow, if I memorize that, I'd probably have them both, don't I? Okay, so, again, last time, this will probably be the last time I do this for you. But, that's stand up. And I do need a little help, so I'm going to ask you to get me a little rhythm. I'll start out the rhythm. You give me just a little back rhythm. Okay, yeah, I need some help here. I'm getting there. I gotta get him. The first thing you do, subtract 32, 5 nights. Yeah. Okay, that's enough. Again, very, very, very short song. And I don't know. I have no idea how I even came up with that over almost 40 years ago, whatever it is. I don't know how it happened, but I do know that I never forget it. First thing you do, subtract 32, 5 nights. Yeah. Okay. Well, anyway, let's go ahead and do that right now. Let's take 98.6 and put it in your calculator. And we do have to be a little careful with the calculator because of order of operations. Remember that? Okay, so if you say 98.6 minus 32, here's what I do. I know what you do. You do parentheses, 98.6 minus 32 parentheses. I'm just a little bit lazier than that. I'll say 98.6 minus 32, enter. So I only press one button. You had to press two buttons, see ya? And then you say times 5 nights equals, enter, okay? Okay, what do you get? The whole world knows that 37 Celsius is normal body temperature, all right? Has anybody been to another country and you were supposed to tell them what you found your temperature? Nobody? No missions? You went?
Yeah.
Where were you?
Ireland.
Ah, and did that come up? Did body temperature come up?
It did at customs.
What in customs?
Yeah.
Ah, what happened? Did they took your temperature?
Yeah.
And it went to 37. They said, "Whoa, I'm freezing." No, what was it?
Yeah, it was around 37.
Well, I have a little story. My son has lived in Bangkok, Thailand, for over 12 years, and he'll tell me, first of all, in Bangkok, they have 2 seasons, hot and really hot. Okay, it's hot there. It might get sort of cool in the winter, a little bit, maybe only in 85, okay? Anyway, so he, of course, they use Celsius, and he said, yeah, we've had 2 weeks in a row, and it's been over 40 for 2 weeks in a row. And he said, what does that mean? Well, I know that body temperature is 37. That's 98.6. So what do you think 40 is? It's over 100. It's way over 100, isn't it? So that's what I use. I use that as my little marker. Okay, let's do a room temperature. You go to Italy and you said, hey, what's the weather going to be like today? Well, I don't know. They told me on the news, but I didn't know what that meant. So what if we did this? What if it was 72, a normal room temperature? Do that. First thing you do is about 32, 5 nights. Yeah. All right, let's do that one. If you went to Italy or Europe, what would be a comfortable room temperature? What are we getting? Anybody got this done yet?
22.2.
Okay, so even though it's 22.2, I'll probably just forget the 2.2 because I won't be able to feel it anyway. Somewhere around 22, right? That's a nice temperature. I like that. That's a room temperature, around 22. Okay, now let's do this one. Why in the world would you pick minus 40? I don't know. Let's try it. Pick minus 40, and minus 40 Fahrenheit equals what in Celsius? Let's try it. What? Did you put it in the calculator? Oh. And here's where, this is where I'm different. I do different than I would in 10th grade. I want you to think about this. If you look at these scales here, way up here, I'm 98 and you're 37. Okay, our numbers are not that close. But then look down here, as this gets smaller, our numbers get a little closer. And then, but I noticed down here for absolute 0, the numbers are far away again. So that means that the 2 scales number-wise are far away, then they get closer, and then they get far away again. There must be a place where they read the exact same number. And that was actually on Jeopardy once. What temperature on the Fahrenheit scale is the same, reads the same on Celsius? It was minus 40. So if you thought maybe you did something in the calculator wrong, that's the only temperature that happens. Okay, dry ice is minus about 110, 109 degrees Fahrenheit. What is dry ice in Celsius? Try that. Now, I gave you a negative number. You got to be careful. You subtract 32 from negative 109. Okay. Raise your hand if you got it. Yes.
Negative 78.
Is that right? Okay, so about minus 78 Celsius, like that. Did everybody get that? Are you okay with this? Now, let me tell you what's going on. I thought the Celsius scale was pretty smart. And they did use water as one of their main events. We had other temperature scales in history, and some of them, we're not exactly sure what they based them on. One of them I actually did think for a long, long time. In a science lab, if you take, have anybody done this? You take ice and you put salt on it. Okay, so let's say you take a baggie, a little Ziploc bag, and you put some milk in there, a little bit of chocolate, maybe some vanilla, shake it up, all right? And then what you do is maybe you put another bag around it, and then you put it into a big gallon Ziploc bag, and you put ice around it and put some salt. And then you close it up, and you just kind of roll it around for about 10 minutes, maybe 15. And you might need a towel because you get a lot of condensation. And it just rolls around, rolls around. Then you take it out, take the other bag out, and you eat ice cream. So you can actually, you can freeze that because ice is cold, but salt and ice will make something even colder. It'll actually get below freezing, and you can actually freeze and make your own ice cream at home. So if you want to do that this weekend, it's pretty neat. The reason I had a double bag is I hate it if salt water gets into my ice cream. So I put it in a double bag, and then I rinse it off and everything like that. So there are some people that said that somebody's scale started because if you took alcohol, ice, and salt, that's the coldest that any scientist could get at the time. Now you have to remember that we did not always have refrigeration. Refrigeration with electricity, get it? We didn't have that the whole time, didn't they? So some scales they thought started there. But another story I read said in this city it was really cold, and they said, well, that's the coldest anybody's ever known this city to get. I'm gonna let that be my 0. And so there's all kinds of stories about temperature scales. But I like the Celsius one because it says water is important to humans. And these numbers are easy, 0 and 100. And I think you would easily fall into this. If we started using that, I think you'd be okay. Okay, now, what happened here is a story around 1960. Around 1960, the metric system, something happened to the metric system. Anybody know what happened? It was in the reading. It was a lot of the things they had defined about the meter and the kilogram. It seemed to work, but technology was going at a good pace in the 1900s. And they eventually figured out this metric system with the meter and the liter and the gram, it's not going to fit. We're discovering so many things that and we want everything to be connected. It's not going to work for us. So we have to modernize the metric system. What do they call the modernized metric system? And that was in the article also. What do they call the modernized metric system? It's usually it's the same. Usually they only use 2 letters to abbreviate it. What is it?
System for the System International?
Yes, the System International, also known as SI. Okay? Now, SI is the modernized version of the metric system, and in that, there are, you probably read, let's see if I can find it here, you probably read that there were 7 base units. Do you remember the 7 base units? Maybe you don't remember all that. Anyway, I'll find that for you. Let's see it here. Wait a minute. I know he's here. Oh, there it is. Okay. I'm going to talk about this later. I may get to today, maybe not. But see right here, these right here are the 7 base units right here. And instead of having meter, liter, and gram, they said, notice that meter, they like the meter, so we're going to keep that meter guy. Liter's not here. Liter's not here because a liter can be defined as a cubic decimeter. I can use the meter to define the liter. So liter disappeared from the SI. Kilograms, not grams, kilograms. Okay, they thought that was going to work better. And then for time, it's seconds. For the number of particles, it's called the mole. Remember the mole concept? That's number of particles. And what was for temperature? They switched out of Celsius and went to what? Kelvin. Okay, and it's not called degrees Kelvin, they're just called kelvins. Everybody get that? Actually, a name for what they call Lord Kelvin. That was actually John Thomson. And John Thomson, he was given, I believe he was ownership of this land that was near the Kelvin River. And he was called Lord Kelvin. But his name was John Thomson. Well, anyway, they decided to name it for his name, Kelvin, okay? Lord Kelvin. Now, what I thought was smart was they said, you know that thing with the Celsius, man, that was good. What you came up with, that was really good. You know, 100 degrees between I like that. So instead of inventing an entirely different temperature scale, they said, we're going to keep using the idea of Celsius. But you know what's really bad? What's really bad about Celsius and Fahrenheit? What's bad about both these? You're going to say, nothing. I like them. But what's really bad is this. Look right here. Look on the scale here. What's 2 times hotter than 0 Celsius? And you're thinking about math class, you said 2 times 0. 0? And then you say, that doesn't sound right. What's twice as cold as minus 10 Celsius? Well, I'm minus 20. What? Is that it? Is that right? What's twice as hot as minus 10? Minus 20? So you can see what happens is, if you have a scale that has positive and negative numbers, you're going to be in trouble mathematically. You try to put that in a math equation, something's going to mess up. You can't even say, what's twice as hot as minus 50? Minus 100? Something's not right, you see? So what they said is, we're going to keep this scale, except we're going to get rid of all your negative numbers. Now, you went down to minus 273, right? We're going to make that 0. Is that okay with you? Okay. Is it okay with you? Anyway, so what happens is this scale, called the Kelvin scale, is also known as the absolute scale because its 0 is also known as absolute 0. Now, that's a theoretical temperature, and yes, there are some people on this planet, some scientists, that are within maybe a billionth of a Kelvin of getting there, but I don't know, will they ever reach it? I don't know. I don't know how they got that close myself. And some people think, what's going to happen if we reach there? Well, maybe we find out it wasn't the right number. But whatever happened, we know that 0 Kelvin, this scale will not have any negative numbers. So guess what? What's twice as hot as 6 Kelvin? 12 Kelvin. Okay, what's twice as hot as 100 Kelvin? 200 Kelvin. See that? And that's why this is going to replace, that's why I replaced this one. Got that? Now, are humans still going to use this in their laboratory? Yes. Humans love numbers between 0 and 100. So if you went to a laboratory, they'll probably be reading things on the Celsius scale, but anytime they want to put any kind of a mathematical equation, they have to convert it to Kelvin. Is everybody with me on this? Okay, yes.
But if you were to say, like, what is 3 times hotter than absolute 0, would that just be like...
Okay, now that would be a problem. That would be a problem for me. Now I could say, what's 3 times hotter than 0.0000001 Kelvin, which is as far as we've gotten, and I would just take that times 3. But you're right. I like your thinking. Even 0 Kelvin, 0 on any scale is not great for mathematics. When you guys do proportionalities, right? You can't use 0, can you? 5 is to 16, as x is to 0. That won't work. That won't work, will it? Okay. So, a great point. Thank you. All right, so what we're going to do is, the good news is, let's look over here. This one's first thing you do is subtract 32 5/9. Yeah. Now look over here, and let's practice this. And I'll tell you why you want to practice it, because you say, I wonder if I memorized it right. What are two numbers in the Celsius and Fahrenheit you're absolutely sure about? Do you know what freezing water is in Fahrenheit? I hope you say yes, because your 11th graders is 32, right? And what about Celsius? So let's see if you have this memorized correctly. If Celsius is 0, and I want to change it to Fahrenheit, what's 0 times 9/5? That's 0, and I add 32. 32. See, I know I memorized it right. That's my check. You see that? Let's try the other way around. How about 32 Fahrenheit? 32 minus 32 is 0. 0 times... See? So if I just memorize that one, I can check myself to see if I memorized the equation right. Now, the other one I think is kind of easy. All you have to do is take the Celsius degrees, take the Celsius temperature, and add. And you don't have to memorize the 0.15 if you want to. You want to impress people, you can do that. But 273 is okay with me. You get that? So you add 273 to Celsius. Let's try this. Well, what's absolute zero in Celsius? Negative 273. What's that in Kelvin? We'll add 273. Doop. That works. What's an ice cube in Kelvin? Let me see how fast you can do this. What's an ice cube in Kelvin? What is it? 273. Ooh, what about boiling water? 373. It's still 100 away, isn't it? So they kept the Celsius scale. They kept the size of the Celsius jump. They just didn't have any negative numbers. They're really the same thing with no negative numbers. So it's not some brand new temperature scale based on something else. All right, and I did this. I may have done this in 10th grade, but I don't know if I did or not. But let's go over here real quickly. And this one, I had hand drawn this, and somebody said they would do it for extra credit, and they tried to make so. So what I had is I had a mountain, and down at the bottom of the mountain I had an ice cold pond. It's an analogy. Okay, there's an ice cold pond, and at the top I had a company called the Acme Water Boiling Company. It's an analogy. Anyway, so at the bottom of here it's freezing water. At the top is boiling water. And my employees were always complaining because they had to walk up this mountain, and sometimes it rained and they slipped. And I said, can't you put some steps in there? And okay. Well, anyway, on this side of the mountain valley, the only company that made steps was a Fahrenheit step company. And so I called them up. Hey, I need some steps. They said, okay, we'll get there, but you're not going to first job. We're going to do a small job, then we'll come out there. Well, they did another job. When they got there, the reason they know how to charge you is they have all their steps are numbered. So they said, okay, we already used the first 31 on another job, so we're going to start with number 32 with you. And when they got done, boop, 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 boop. When they got done, they went to 212. Everybody got that? It's an analogy. Okay. Then, so what happened over here, and they couldn't get over here. There was no gap in the mountain range. So the only company that made steps on this side was the Celsius company, and they made their steps different than you did. They said, oh, you're the first job for us. We'll be right there. And their step number 0 was there. And then they started here, and they ended up with 100. So, everybody see that? Okay, now, here's what I want you to do. In here, we talk about ratios a lot. I think that's where most people are weak. Some of the best stuff in science is in the world of ratios. Now, sometimes you won't catch on to it right away. Look at me. You won't catch on to ratios right away because you haven't been forced to do this all the time. I'm going to make you do it all the time. Look about ratios, okay? So right here, tell me how many steps they were charged for. This is not a ratio. This is subtraction. They were charged for 180 steps. And they were charged for how many? Well, that means which step is a bigger step? Which company's step is bigger? It has to be Celsius because I only needed 100. I only needed 100 of their steps, didn't I? So which one is a greater jump in temperature, a 10-degree jump on the Fahrenheit thermometer, or a 10 degree on the Celsius? It's Celsius. And I'm talking about ratios, wasn't I? In the world of ratios, what's 100 over 180? And what's 180 over 100? Let's look. What's the ratio of the step size? And you said, thank you. That made my day. What is it? Oh. See that? A lot of people, they don't know where that number comes from. One thing that disappoints me a little bit, in my chemistry, even in my advanced chemistry book, they have the equation like this. Fahrenheit minus 32 times 0.555. And unfortunately, you can memorize that, but guess what? You lost the idea of where it came from. And the other one will say like this. It'll say Celsius times 1.8. 1.8 times Celsius. Again, 9/5 is 1.8. 5/9 is that. So I think you lose the idea. I like still teaching it with the fraction because I actually know where they came from. Are you with me on that? All right. Well, and again, so which one's better? Which one's a bigger jump in temperature? A 10 degrees Celsius jump, a 10 degree Fahrenheit jump, or a 10 Kelvin jump? Oh, I threw something else in there. Which one's the biggest rise in temperature? 10 Fahrenheit, 10 Celsius, 10 Kelvins? Somebody. We already know that Celsius, 10 Celsius is a bigger jump, isn't that right? Now, is it Celsius or Kelvin? They're the same. Tricked you, didn't I? Okay, so anyway, if you go up 10 Celsius degrees, that's the same as going up 10 Kelvins. All right. Okay, I'm a little bit further now. I'm going to go back, excuse me, this page here. And this one, I just want to tell you a tiny bit of history, not a lot. It said here, this is a summary of the temperature scales. Number one, the Kelvin scale is the SI unit for temperature. SI is a modernized metric system, right? The Kelvin scale is also called the absolute scale, and 0 kelvins is absolute zero. The Kelvin scale units are the same size as the Celsius scale units, so a change of 25 degrees Celsius is the same as a change of 25 kelvins. Does that make sense to you? Okay. There are no negative temperatures on the Kelvin scale. That's good. Almost all chemistry and physics equations dealing with temperature require you to convert to Kelvin. I wouldn't even teach it to you if we didn't have to have it. The Fahrenheit scale was named for, that's like Gabriel Fahrenheit, yeah. I mean, that's his name, Fahrenheit. The Celsius scale was named for, his name was Celsius, Andrew Celsius. And the Kelvin scale was named for John Thomson, also known as Lord Kelvin. There you go. There's only one temperature in which Fahrenheit and Celsius thermometers read the same number. You already found that, didn't you? How many temperatures will give the same number for Celsius and Kelvin? None. They will always be 273 apart, won't they? And then the other one, if you like mathematics, this is a neat little puzzle. I'm going to try it. How many temperatures will give the same as Fahrenheit and Kelvin? If you look, 0 Kelvin is minus 460 Fahrenheit. But when you get to an ice cube, 273, 32. They're getting closer. See that? That means they're getting closer. There must be some place where they're going to cross. So if you like mathematics, see if you can figure that one out. I know some of you are going to say, I got a smartphone. Okay, you could do that, but it's a little more fun mathematically. See if you can do it mathematically. There's that one. All right, so let me, I only have about 30 seconds here. Here's what you're doing. Besides looking over the packet, I want you to do the robot thing. It's kind of fun. You got 3 days to do it, right? I know you could do it. Turn it in on Monday. Now, and then what I'm going to do is I'm going to try to wrap up everything on Monday. I am going to talk about that chart I just showed you, the SI chart, and you don't have to memorize that chart. I will give you that chart. You just have to know how to read it. So I'm going to show you how to read that chart. So the 2 things I'm going to do on Monday, read the SI chart, know how to read it, and then also we'll talk about common metric units. Can you estimate, if I say, could you estimate a kilometer? What would you do? Well, first of all, it's going to be 1,000 meter sticks. That's about 6/10 of a mile. So if you said, I'm going to go a little more than half a mile, that's a kilometer. So I want you to feel comfortable with metric units. I'm sorry.
You have to fill out the whole